Alright, today's video lesson is going to focus on double replacement reactions. Essentially what we're going to be doing here is going to be looking at predicting products for various chemical reactions. And the first one we're going to look at is a double replacement reaction. And in order to determine the products of a reaction, you're going to have to be able to identify the type of reaction that it is. Okay, so for a double replacement reaction, what's happening is that we're going to have two ionic compounds that are going to switch cations, or you could think about it switching anions, depends on what you want to do. I prefer to just focus on switching cations around. But if we look at the reaction, okay, just picture this products part not here, we'd have two compounds, one cation, one anion, one cation, and one anion. The general form of a double replacement reaction is that these two ions are going to switch places. So you're just going to rewrite them in front of the x and the y. So you get a bx and an ay as opposed to an ax and a by. Alright, so it's kind of sounds silly because we have a's and x's in here, but it would look something like this. If you have something somewhat like lead, let's just say we have lead nitrate. So let's say we have lead 2 nitrate. And it's going to be really important to write that balanced formula properly. So what we did in the last chapter with balancing the formula, it's going to still have an impact here. And let's say we have something like lithium chloride. Okay? And we react these two together. We've got our cations. Use a different color here. So we have our cations, and we're going to just switch these and replace them. And that's pretty much it. So the trick here, though, is to watch the charges now. Okay, one thing that happens when you write the products is that the charges on these ions do not change. So we have here is lead. Actually, let's rewrite that as lithium. Lithium now takes the place of lead, which has a positive 1 charge because it's a lithium element. Lithium nitrate plus lead chloride. Lead has a 2+ charge based on the 2 here, and the chloride is a -1 charge because it's a halogen, and then we balance the equation. So then I'm going to put a 2 right here to balance my lithium and my chlorides. Okay. And then I have to balance the lithium on this side. So now I have 2 lithiums, 2 nitrates, 2 nitrates, 2 lithiums, 2 chlorides, 2 chlorides, and 1 lead. Okay, so if you have trouble balancing, it's gonna, definitely have a role here. So make sure you go back and review the video on balancing equations if you need to. Okay, so hopefully you noticed the pattern here, just switching those anions around. Okay, so let's take a look at the reaction a little bit closer. Let's take a look at another example. Let's say that I have sodium, let me try that again. Silver nitrate, and it's aqueous, and sodium chloride, aqueous. Now aqueous, what that means is that this salt, or this ionic compound, is actually dissolved into water. So keep in mind that what that means is that those ions are free to move around. So you got ions that are in here moving throughout the solution. Sodium chloride, we have the same thing. So everywhere you see AQ, you're going to have ions that are free and mobile throughout the solution, and we saw that with the conductivity of the light bulb. Now, if we mix these two solutions together, they're all going to come together in the solution. Okay, so what we want to look at here is what are the possible scenarios that can play out when we mix these together. Is it possible for the sodium and the silver ions to come together? Well, if you look at the positive charges here, hopefully you can conclude that that's not going to happen. Okay, now over here, okay, we're going to have 2 negative ions, and those aren't going to come together. Okay, now we could have the sodium and the chlorine come together, but when they come together, they stay dissolved in the solution. Okay, and then if I have the silver ions and the nitrate, well, we know again that those are aqueous. Okay, so what happens here is that that silver ion and that chloride ion are going to come together, and essentially what's going to happen is you're going to get the solid to form. Okay, so what we're looking for double replacement reactions is we're looking for the formation of, well, technically, let's back it up here for a second. What we're looking for is the removal of ions from solution. That's crucial, to a double replacement reaction. Removal of ions from solution. Okay, so when we mix these two reactions together, these two chemical compounds together, what we end up with is a solid substance that forms. So beforehand, it looked like this, and then we mix them together, you end up with this, where these two ions come together. So we're looking for the removal of ions from solution. And there's two ways that this is going to happen. One, formation of a solid. Okay, formation of a precipitate. Oops, let me try that again. Don't why am I so trouble writing that? Precipitate, which is essentially a solid. So a precipitate is a solid. You've seen this already in a couple labs that we've done, and we'll look at more as we do more labs. But we're looking for the formation of a solid substance. Okay, and we'll talk a little bit more about that in a second. And number two is the formation of water. And we're going to see that in the next set of reactions. Okay. So we're looking for the formation of a solid, or we're looking for the formation of water. Essentially, with a double replacement reaction, what we're looking for is the removal of ions from solution. Notice that the solid now, those ions aren't free to move throughout the solution. They're locked in a solid phase and can't get out. They're kind of trapped in that solid. So those ions are now pulled from the solution and can no longer react. So this is the way it looked like before. Those ions were free to move in the solution, and now, boom, they're gone. So, how do you know if a reaction is going to form a solid or not? Well, first thing you want to do is rewrite your products. Okay, switch your ions just like we did before, and then what you want to do is you want to look at the solubility of your solids, right, or your substances that you created, and look for a solid. So if I look at my solubility rules, which is what I'm going to need for that, my solubility rules are going to tell me whether something is solid or not. Now remember, there's that other set of solubility rules where I said, if you remember that one, all alkali metals, so sodium, lithium, potassium, and essentially any of the other alkali metals, and ammonium. Those are always aqueous. Okay, and number two, nitrates are always aqueous. If you remember those two, you can probably pretty much get this every time. But if you focus on, if you use the chart, you can use it, it's fine, it's up to you. So notice that a lot of silver compounds are insoluble, okay, except for dichromates and nitrates, right? So those are the two that are, so anything else with a silver, so we're cross-referencing chloride and silver, we see that it's insoluble. Insoluble means that it would be a solid. If I cross-reference sodium, well, everything in sodium is soluble based on rule number 1. So therefore, what you would do is you would rewrite your products, okay? Write the products out and then look at whether they're soluble or insoluble. If it's insoluble, then you have a reaction happening, okay? So let's take a look at another example. Let's say that we have okay, so we have copper sulfate, and it's aqueous, and we're going to have copper sulfate reacting with sodium sulfide aqueous. Okay, so I'm going to take this reaction, and I'm going to rewrite my cations and switch them around. So what I end up with is sodium sulfate, and I got to remember to write my reaction, balance of charges, and then I write over here copper. Now the copper has a positive 2 charge based on that sulfate. Sulfur has a -2 charge, so I'm going to get copper sulfide, okay? Copper 2 sulfide. Alright, so then I go back and balance the equation. I have 2 sodiums, sulfur, so everything's balanced. If you notice real quick, it's, if you need to, go back and double check, but I know it's going to be balanced. So the next thing to do is to use my solubility chart, and what I want to do is look at these two substances here. Are they aqueous or are they solids? And what you're looking for is a precipitate or an insoluble substance. So obviously all sodiums are aqueous. Then I look at my coppers, and I'm looking for copper and sulfur. Copper and sulfur is the last one, so copper insoluble. Okay, so therefore, since it's insoluble, I know that this is going to be my solid, and this is going to be my aqueous. And there you go. There's your double replacement reaction. Okay, let's take a look at one more. Lithium, we'll do some more examples in class. So lithium chloride, aqueous. Let's say it's reacting with barium let's say barium nitrate. Let's say that'll be aqueous as well. And most of the time your ionic compounds that are reacting, they have to be aqueous. You're almost always going to be dealing with two solutions that are going to be poured together. Alright, so I'm going to have barium and a barium chloride, which would be a 2. And, no, that's not what I wanted to do. Shoot. That's okay, I'll do one more after this. Okay, and then we have lithium and nitrate. Okay, right away I know that this is going to be aqueous because of the lithium and the nitrate rule that I told you about before. So the only thing I really need to look up is that barium. And barium and chloride, oh good, that's what I wanted. Barium and chloride are soluble. So therefore, if that means they're soluble, that means that this is going to be aqueous. And it's going to work out exactly what I wanted, which is good. Alright, so if that's aqueous, there's no solid, right? No precipitate that is formed. I don't know why it slows down when I write that word. Okay, so no precipitate formed, right? No solid, so therefore no reaction occurs, right? Because if we think about the solutions, you've got lithium, right? It's in solution, and the chloride's in solution, right? And you have over here barium, which is now in solution, and you also have the nitrate in solution. Now on the other side, how is it any different? What's changed? Well, barium's in solution, it's aqueous. Chloride is in solution, it's aqueous. I don't need to write AQ, but and my lithium's aqueous, and nitrate's aqueous. So if we compare the before ions and the after ions, nothing's changed. So therefore we would say no reaction. RxN is my abbreviation for reaction, so in case you're wondering what that was. But that's pretty much it for balancing or for double replacement reactions. So we'll talk about them in class and look at them again. But one last slide I'll put up here is a little step-by-step account on how to do, write double replacement reactions. First thing, write out the products by switching the ions. 2, balance each formula. Very important. A lot of students miss that step. And step 3, check the solubility. And of course, don't forget to balance the entire equation. Okay? So we'll look at a little bit more in class, and I'll see you later.